we saw the properties of a field and the properties of an ordered field, among things. And now we will start looking at the title of the chapter, which is Real and Complex Numbers, right? So let us start with the field of real numbers. The field of real numbers. Field of real numbers. Okay, so first of all, the construction is slightly annoying, and we will look at it slightly later, but we will for now say that the field of real numbers exists. There is an ordered field. There is an ordered field R which contains the sorry, which has the least upper bound property, which has the least upper bound property and it contains Q as a subfield. Moreover, R contains, so let me denote R by our standard notation for R. Moreover, R contains Q as a subfield. As a subfield. Okay. Now, proof we will do later. We will do later. Okay. But for now, we are going to assume that that R is an ordered field which contains Q and it exists. Now, there is a slightly important implication of what the statement means. The second statement means R contains Q as a subfield. R contains Q means that the operations of addition and multiplication in R when applied to Q, that operations of addition and multiplication on Q, sorry, on in R when restricted to Q, when or applied to Q, and applied to members of Q, coincide with the operations on Q. With the operations on Q. So it is more or less saying that we can extend our field Q to a field R such that all the rules that we had in Q, the properties of Q, they should be able to generalize. Okay, not every single property is going to generalize, but we should be able to generalize the addition and multiplication from Q to R. We have already shown most of the properties that hold for a field actually just hold for fields, and ordered fields generally hold for everything. So we are not going to show them specifically for R. And then we are going to jump into a theorem, which in the book is I think 1.20. Let me just write it as 1.20. A. If X is in R, Y is in R. If X in R and Y in R, and x greater than 0, then there is a positive integer n. There is a positive integer n such that nx is greater than y. Nx is greater than y, and this is called the Archimedean property. So this is referred to as the Archimedean property of R, Archimedean property. Okay. Now, while this property might sound a bit silly, saying that, oh, of course, as long as that number is positive, you can always multiply by something big enough to make it bigger than every other number, this property has some really important consequences. And that is why it's something that needs to be specially mentioned, and it has it's important enough to have its own name. So while it sounds trivial, it is not. If x is in R and y is in R and x is smaller than y and x smaller than y, then there is a P in Q, so rational, such that x is smaller than P is smaller than y, which is to say rationals are dense in reals. Q is dense in R. Okay? Proof? Well, so let us look at the set. Let A be the set nx of all nx of all nx, where n runs through n, where n belongs to the natural numbers n. Okay? So now if A were false, if A is false, that means that there is then y is an upper bound of A. Then y upper bound of A. Upper bound of A. Bound of A. Well, it is a non-empty bounded set, therefore let alpha is equal to supremum of A. Okay? And since x is greater than 0, and x times 1 is definitely part of A, we have that alpha minus x, which is still positive, is smaller than alpha. Sorry, alpha minus x is smaller than alpha. Since x is positive, I did mention x is positive, right? Yeah. Since x is positive, alpha minus x is positive, greater than alpha. Less than alpha, and alpha minus x, therefore, is not an upper bound of A. Is not an upper bound of A. Well, if it was, then it would be the least upper bound, right? Contradicting that alpha is the least upper bound. Therefore, since this is an upper bound, this is not an upper bound, there is some m. There exists m in n such that alpha minus x is strictly smaller than mx, right? Whoops. Which therefore implies that alpha is smaller than mx plus x, which is equal to m plus 1x. contradiction, m plus 1 x, contradicting alpha was the supremum. Okay, and so such a supremum cannot exist, and that is why we have that this set is unbounded. Okay, and that allows us to do part B. Since x is smaller than y, I have that y minus x is greater than 0. Okay, and therefore, by part A, there exists some m, in n such that m times x minus y is greater than 1. Right? Let me why okay. Actually, let me call this n, because my fraction that I've written, fraction is generally going to be m over n, so I want this to be n greater than 1. Okay, once again applying 1 again by A, I have that there exists m1 and m2 belonging to n such that m1 is greater than nx and m2 is greater than negative nx. Okay, therefore what that means is negative m2 is strictly smaller than nx, which is strictly smaller than m1. Right? Therefore there exists m in n such that with m1 smaller than or equal to m negative m2 smaller than or equal to m smaller than or equal to m1, why can't you just scroll properly? Okay, such that m minus 1 is smaller than or equal to nx is strictly smaller than m. Right? I can find my m within this. I can find my m such that nx lies between this interval, and therefore combining the two, we get that nx is smaller than or equal to strictly smaller than, well, it is strictly smaller than m, but nx is greater than m minus 1, greater than or equal to m minus 1, so this is strictly greater than greater than or equal to 1 plus nx, right? Adding 1 to both sides here. And well, nx is smaller than ny, so I get this is smaller than ny. Right? And so I have that nx is smaller than m is smaller than ny. Therefore, x is smaller than m over n is smaller than ny. Okay? So for any two real numbers, you can always find a rational between them. Right? P is equal to m over n. Okay? So for any two real numbers, even if they're rational or not rational, it doesn't matter. You can always find a real number between them. Sorry, you can find a rational number between them. Okay, that's theorem 1.20. Let's look at the next theorem, 1.21. This says for every real number greater than 0, for every real number x greater than 0, and every integer n, and every integer n greater than 0, there is a unique positive real number. There exists unique, well, let me just write it in words. There is a unique y, positive real y, unique positive real y, such that y to the n is equal to x. Okay? Proof. Note, everything is only working with positive. So even though, for example, if you take x is equal to 2, x is equal to 4 and is equal to 2, when you will, and you know that, oh, negative 2 as well as 2 are squared to 4, since we are only dealing with positives, it will only be 2. Okay? This number y will be written, y is written as nth root of x, or x to the 1 over n. Okay, so this is what we want to define. Okay, so now, since we are dealing with positive real numbers, the fact that there is such a number is unique is pretty easy. That there is at most one such n, that there is at most one such y is clear as 0 smaller than y1 smaller than y2 implies 0 smaller than y1 to the n smaller than y2 to the n, and since this is an ordered field, every two numbers are comparable. Okay, there is a total order, every two numbers are comparable. If there were two such y's, one of them would have to be larger than the other. Okay, so now here we start using the least upper bound property of R, right? So let E be the set. Let E be the set of all positive real numbers t such that t to the n is smaller than x. So t belonging to R such that t to the n is smaller than x. Okay, what we want to show eventually is that supremum of E is equal to y. Okay, so what do we need to show for that? We need to show that it is non-empty and bounded, right? So if t is equal to 1, if t is equal to x over 1 plus x equal to x over 1 plus x, then t to the n, then first of all 0 is smaller than or equal to t, 0 is smaller than or equal to t is strictly smaller than 1, right? Therefore t to the n is smaller than or equal to t, and because I'm dividing by 1 plus x and x is positive, this is also strictly smaller than x, right? Therefore t belongs to E, and therefore E is not equal to the empty set. Okay, so we have shown that it is non-empty. If t is greater than 1 plus x, right, then t to the n is greater than or equal to t, well, which is greater than x. And therefore t is not in E, Okay, and so it is an upper bound of E. Therefore, T is an upper bound of E. T is an upper bound of E. Therefore, E is bounded above. Great. If T is bounded above and it is non-empty, therefore E has a supremum. Therefore, let Y is equal to satisfies Y to the N is equal to E. This is what we want to show. So let Y is equal to supremum of E. Then we want to show that Y to the N is equal to, so the part that is left now to show is Y to the N is equal to, not E, this should be X. Okay, we still need to show that Y to the N is equal to X. And the way we are going to show is, we'll show Y to the N is greater than X and Y to the N smaller than X lead to contradiction. Okay, so first notice that B to the N minus A to the N is equal to B minus A times B to the N minus 1 plus B to the N minus 2A plus dot 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 plus BA to the N minus 2 plus A to the N minus 1. Okay, and therefore if I assume that if 0 is smaller than A smaller than B, then B to the N minus A to the N is strictly smaller than B minus A times, well, there are exactly n of these terms. The largest one is B to the N minus 1, so I am going to say this, all of this is smaller than B to the N minus 1. Okay, well, so assume Y to the N is smaller than X, then choose H choose H such that 0 smaller than H smaller than 1 and H is strictly smaller than X minus Y to the N all over N times Y plus 1 to the N minus 1. Okay, it is always possible to do this because reals are rationals are dense or reals are complete, whatever you want to do. Okay, then letting A is equal to Y, B is equal to Y plus H, we get, let me just write this as star. We get from star that Y plus H to the N minus Y to the N is strictly smaller than, well, B minus A, which is just Y, which is just H, times N times Y plus 1 to the N Y plus H to the N minus 1, Y plus H to the N minus 1. Well, this is strictly smaller than, since H is strictly smaller than 1, let me write it this way, this is strictly smaller than H times N times H is smaller than 1, so this is smaller than Y plus 1 to the N minus 1. And I also know that this is strictly smaller than Y minus H to the This should have been an N, not an H. H is smaller than x minus y to the n over n times blah, blah, blah. Things cancel. This is strictly smaller than x minus y to the n, contradicting that, well, let me just say it out. Therefore, y plus h to the n is smaller than x. Therefore, y plus h belongs to E, contradicting y is equal to supremum of E. Okay. Well, so now we assume that the other way is true. Assume y to the n is greater than x. Well, the idea is going to be exactly the similar. Let k is equal to y to the n minus x over n y to the n minus 1. Okay? So now, with this, we are no longer guaranteed that it's smaller than 1. Okay? But we can say that then 0 smaller than k smaller than y. Okay? Because what is the total fraction? If you divide everything by y, so if you try to pull out the power of y from top and bottom, you'll get y to the n minus something something over y to the n minus 1 minus 1 or something something. So all of it is over y. So the power of y is just 1. Therefore, if t is greater than or equal to y minus k, we get y to the n minus t to the n is smaller than or equal to y to the n minus y minus k to the n, right? Because t is greater than that. Well, now this is strictly smaller than k times n times y to the n minus 1, because y minus k is just k, and this is equal to, because of my value of k, y to the n minus x, right? Therefore, t to the n is greater than x, and t does not belong to E. What that means is, therefore, y minus k is an upper bound of E, of E. Well, that's a problem. But y minus k is smaller than y, which means, therefore, contradicting that y is equal to supremum of E, or it is the least upper bound. Okay? i.e. least upper bound. Okay, therefore, if it's not greater than or equal to x, therefore, as y to the n, therefore, y to the n has to be equal to x, as it is not greater than x or smaller than x. Okay? Corollary. If a and b are positive real numbers, if a and b are positive real numbers, positive reals, then, and n is a positive integer, and n belongs to n, then AB to the 1 over n is equal to A to the 1 over n times B to the 1 over n. Proof. Idea is going to be really simple. Commutativity works in reals, right? And so let let x is equal to A to the 1 over n, y is equal to B to the 1 over n, then AB is equal to both x to the n, y to the n. Well, that is also equal to xy to the n, right? Because x and y are reals and they are commutative. As reals are commutative. R is commutative. Commutative under multiplication. Okay, and therefore the uniqueness shows that, therefore by uniqueness AB to the 1 over n is equal to xy is equal to A to the 1 over n times B to the 1 over n. Okay, now one small note: decimals. How are we going to write decimals? Decimal is let x greater than 0, let n naught be the largest integer k, be the largest integer such that n naught is smaller than or equal to x. Okay, having chosen n0 dot 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 n k minus 1, similarly in the next property, choose nk largest such that n0 plus n1 over 10 plus n2 over 10 squared plus dot 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 nk over 10 to the k is smaller than or equal to x. Right? Then let us say let E be the set of these numbers. Let E be the set of these numbers. Be the set of numbers n0 plus n1 over 10 plus dot 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 nk over 10 to the k, where k is equal to 0, 1, 2, and so on and so forth. Then, because this is a bounded set, it is bounded above by x, right? All of it is bounded above by x, and by Archimedean property, there is an x naught. That's right, there is an n0. It has a supremum. Let x is equal to supremum e. Then the decimal expansion of x is the decimal expansion of, okay, so this is not let, this is then, sorry. Then x is equal to e. Let me just say this. Prove this. Prove this. Okay. The proof is really simple. It's just direct application of Archimedean property like once, but I want you to still do it. The decimal expansion of x is n0 dot n1, n2, n3 dot dot dot. Okay. We are never actually going to be using these. Okay. we are never actually going to use the decimals, so we are not going to be super bothered about it. All our calculations will always have precise values for reals. Okay. Let me do the extended real number system, and stop there. Extended real number system. So what is the extended real number system? Well, definition. The extended real number system, real number system consists of the real field R and two symbols plus infinity and minus infinity. These are not real numbers. Okay, plus infinity and minus infinity are not real numbers. We preserve the order on R. We preserve the order on R and define negative infinity is smaller than R is smaller than X, smaller than positive infinity for every X in R. Okay, that is my definition of infinity and negative infinity. So keep in mind, these are not actual numbers. Okay, so any set that is not actually bounded can have, so note, for an unbounded set E, we can say supremum of E is equal to infinity, positive infinity, in the extended system. Okay, now the extended real number system is not a field. First, second, extended system is not a field, but for convenience, i.e. and convenience, we follow the notation, we use the conventions that A, if R is real, if X belongs to R, then X plus infinity is equal to plus infinity, X minus infinity is equal to negative infinity, X divided by plus infinity is equal to X divided by negative infinity is 0. Okay. B, if X is greater than 0, then X multiplied by plus infinity is equal to plus infinity, and X multiplied by negative infinity is equal to negative infinity. And C, if X is smaller than 0, then X multiplied by plus infinity is equal to plus infinity, minus infinity, and X multiplied by negative infinity is equal to positive infinity. Okay, so these are the definitions that we are using, and everything in this extended system which is not negative infinity or positive infinity will be called finite. Okay, I'm going to stop this video here. We'll look at complex numbers in the next one.